Before I talk about synthetic division, let's actually look at division algorithm with just numbers, like in arithmetic, simple arithmetic. When we divide 17 by 3, now I'm thinking long division. With long division, true 17 is the numerator, 3 is the denominator of the fraction, but when it comes to long division, we change the terminologies for 17 and 3. 17 becomes what we call the dividend, kind of like in stocks, and 3 becomes the divisor in long division algorithm. So how do we actually divide 17 by 3? Well, 17 by 3, we look at how many whole groups of size 3 can I place in 17, and that would be 5. 5 times 3, 15. And we have a remainder in this case, right? Notice I subtract, it was 15, but then we change sign on 15, make it negative, because we subtract 15 from 17 to see how many individual 3's remain in the division. So this would be the remainder, and of course 5 is now called a quotient. So you're looking at the anatomy of a long division. Therefore, in general, we can write the ratio of 17 to 3, the division of 17 to 3, as a quotient 5 plus a remainder over a divisor, right? 5 2/3, which oftentimes is written as a mixed number here. But for the work we do, we don't care about mixed number. Actually, we are interested in this form of the answer. So I can write the answer, therefore, as a quotient 5 plus a remainder of 2 divided by a divisor, right? So this would be how we can rewrite that division problem. Now we want to extend this to algebraic expressions. So in general, suppose now I'm doing the division of f of x by g of x. Suppose I'm doing that division, f of x by g of x. So this would be again a dividend over the divisor, and that's going to be a quotient. The quotient, we're going to call it q of x. The remainder, r for remainder of x over the divisor, which is g of x. And again, I have all these expressions because all these f, g, q, r, these are going to be algebraic expressions. And there you have it. Now, if I multiply throughout by g of x on both sides, do g of x on the left, and then do g of x on the right side. Remember, this is q. Do not mistake those. This would be g, this is q. So there are two different functions. G of x, those cancel. So the left side, f of x, the function, g times q multiplies, right? So I can write it as a divisor times the quotient plus a remainder, because g of x cancels on the right side. But it does distribute to q of x. That's how I got that term. All right, perfect. Now, this is actually interesting. So what this tells us is that every function, f of x, we're talking about polynomial function here, by the way, and let me just say f over g is a rational function. Okay, so the assumption is we have a rational function. So we can write the dividend, the numerator, which is the function, we can write it as product of two different functions, possibly, plus a remainder. Now, in this work that we are doing, notice the degree. What turns out is that the degree of the remainder is either 0 or less than the divisor. So let me just put that, because of that long division that we do. So the degree of the remainder, r of x, the polynomial in x, is either 0, meaning no remainder, or it would be less than the divisor. So that's important to note. And that is less than the degree of, I should say. Less than the degree of the divisor. Now, synthetic division is an efficient way of dividing polynomials by binomials that are in a certain form. Okay, and that is the subject of this lecture and this section. So I'm looking at synthetic division now. So what is synthetic division? That's when we are dividing a polynomial in X, polynomial, call it f of X, by a binomial. The binomial acts as g of X for us, and it has to be in the specific form. It's going to be X minus, again, the minus sign is important here, okay? X minus K. Some go X minus C. It doesn't matter as long as it's a constant. Call it K. Okay. So that's all it is. It has to be divided by a binomial like that. It cannot be like X squared plus K. We're not looking at this kind of a binomial. It has to be a linear function exactly in this form. So how is this going to work? And now the whole process is a lengthy process that I could draw analogy to the process of long division with numbers, go through a whole page, and it will take about 10 minutes, 15 minutes. But I just want to show you the synthetic division algorithm or procedure through an example, okay, without going through details of why it works. So suppose I want to divide 5x cubed negative 6x squared negative 28x minus 2. Notice it's a polynomial function divided by x plus 2. So I have a polynomial function over a polynomial. This is a rational function. Now in the form x plus 2, that would be x minus negative 2. Therefore, this is what k is, right? Or c is. Doesn't matter again what we call it. That's my k. So here's how this synthetic division algorithm works. I'm going to start with, we're going to create a table here, a very short table. The table is going to have all the coefficient on x terms. So we go 5, negative 6, negative 28, negative 2. If a term is missing, for example, if that term was missing, you still have to actually put a 0 for it as a placeholder. Okay? So you can't skip over it. Every term must be listed. The missing terms will have 0 in this table. Next, we're going to put our k here, which is negative 2. Not 2, but negative 2, because the form is in the form x minus k. That's important. Now, how is this going to work? We're going to bring the 5 down. We then multiply negative 2 times 5 becomes negative 10. And we're going to add negative 10 and negative 6 in columns. We get negative 16. We then multiply negative 2 by negative 16. We get 32. And then add 32 and negative 28. We get 4. And next, negative 2 times 4 is negative 8. And we add those two. We get negative 10. And we are done. The negative 10 is the remainder in synthetic division, or in the long division, really, because remember, synthetic division is an efficient way of doing long division without going through all the details. Now, I started with a third degree polynomial in the numerator because we divide by the binomial, so the quotient is going to have a degree that is 1 less than what we started with. So in other words, this is the quotient. This is the quotient in the long division, and its degree is going to be 3 minus 1 or 2. 3 because the degree of this term is 3. You see that? The leading term is a third degree. And in other words, at this point, I can write f of x as, remember the general form was g of x times q of x plus a remainder of x, a remainder of x, r of x. There, and let's try it. G of x is the denominator, x. There you have that. That's my g of x. That's x plus 2. So this would be x plus 2 times quotient. This is q of x. And that's going to be 5x squared negative 16x plus 4. Okay. And then, of course, plus a remainder of negative 10. And that's how we can write it. And you can try it if you distribute here. Let me do that real quick. I get 5x cubed negative 16x squared plus 4x. That's when I distribute x to all three terms, then distribute 2 times 5 would be 10x squared, negative 32x 2 times 4 is 8, minus 10, bring the 10 down. And adding columns, I get 5x cubed negative 6x squared, negative 4x minus 2, right? Let's see, 5x cubed, yeah, minus 32 and 4, sorry, not 4, that would be 28x minus 2. And hopefully this is what we started with. It is. See, I got 5 negative 6 negative 28 negative 2 5 negative 6 negative 20 negative 2. See how it works. And this is indeed my f of x, which is the numerator or the dividend in the work that we are doing. So this was just to verify that it works. Now, if the remainder is 0, by the way, if r of x is 0, then f of x is simply a divisor times a quotient. And notice, this would be now in a factored form. Isn't that cool? And that is factored because we are able to write some difference of terms as product of polynomials. Perfect. So that's what synthetic division is. Now, as you just saw from this example, by the way, when we do synthetic division, the remainder is the number at the end, right? In the third row of synthetic division table. Now, if that remainder is 0, we just mentioned that the polynomial, the numerator, can be written in factored form. So we actually can now cite our theorem here. This theorem known as the remainder theorem, rightly so. And the theorem goes something like this. If f of x is divided by x minus k, remember it has to be the binomial in that form. If a function, f of x is polynomial, by the way. Remember, everything we do in this chapter, in this whole work right now, is polynomials. So if a polynomial is divided by x minus k, and the remainder is f at k. So let's try and see what this is telling us. Let me give you an example of how this remainder theorem works. So I'm going to make up a polynomial function here. If f of x, for instance, is negative x to the fourth plus 3x squared negative 4x minus 5. And suppose we want to find f at negative 3. Okay, so here k is negative 3. All right, so instead of, here's how we should do this without long division or without synthetic division for that matter. To do f at negative 3, I have to put negative of negative 3 to the fourth plus 3 times negative 3 squared minus 4 times negative 3 minus 5. So I got to do a bunch of arithmetic here, right? Which it could, and this will make it negative 81 plus 27, 12 minus 5. The whole thing is negative 47. Right? Now, that's the answer, but let's do this using synthetic division. And for synthetic division, here's negative 3. And my synthetic division table will be coefficient on x to the fourth, coefficient on x cubed. X cubed is missing 0, right? See, there is no x cubed. So that's a 0. Can't skip it. Then it's coefficient on x squared, on x term, and the constant. And the algorithm begins. So we bring the negative down. Multiply negative 3 times negative 1, we get 3, and then add with 0, we get 3. Remember, we add in columns. Next, you're going to do negative 3 times 3. That's going to be negative 9. And then add, we get negative 6. Then we multiply negative 3 times negative 6. We get 18. 18 and 4. Negative 4 makes 14 positive. Negative 3 times 14 is negative 42. And add negative 5 to that, you get negative 47, which is the remainder. And there you have it. So that's what the remainder theorem does for us. It only works though if you divide by x minus k. So you can, if you don't do that, then of course it's not going to work. But then for any polynomial function, if they want to evaluate it at a point, rather than plugging this in, we can do synthetic division. It will go probably a little faster, maybe not. Either way, it works. Okay, so that's what that is. Remainder theorem. All right, so let's take a look at the proof of the remainder theorem. So what I have here is I have f of x is equal to, you can write, remember, any function as product of a quotient, that's what q of x is, times a divisor plus possibly a remainder. Now, for the proof of remainder theorem, if g of x, we let g of x be x minus k, in other words, this divisor here, the degree of this x minus k is 1. Now, because we are dividing in a long division by x minus k, the divisor, therefore the remainder either will be 0 or has a degree that is less than the degree of x minus k, the divisor, because the degree of x minus k is 1 again. So that means the degree of remainder has to be 0 if there is a remainder. A 0 degree polynomial is a constant. So I went ahead and said r of x equal to simply r, a constant. Now, if I evaluate the function at x minus k, right up here, if I evaluate the function at x minus k, I have f at k is equal to, replace x with, right up here, replace x with k, and then from this, we'll be able to see that the product is going to be 0 times q of x plus a remainder, and we get the proof of the remainder theorem. Pretty easy. Now, the zeros of polynomial function have also other AKAs. They are also known as the following. So remember, when we say 0, we don't literally mean 0, although it could be, but it doesn't have to be. In this case, for instance, I have x equal negative 5, which is solution to that function. Therefore, the 0 here is actually x equal negative 5. Okay. Now, in item number 1 here, when we talk about 0 of a polynomial, that means x equal k is a 0. That's the value that gives you 0 for the function. And x equal k is a solution of that equation, actually. Number 3, x minus k is a factor, and we can see that again from up here. This is a factor because it's being multiplied by q of x, the quotient. Also, the point k, comma 0 is an x-intercept of the graph of the function on the graph. Okay. Now here I have an example. And we want to determine if k equal negative 1 is a quote-unquote 0 of this 4th degree polynomial function. So we can see that this one, I have the answer, no, it's not a 0, because what we do is we do a synthetic division of the polynomial by k. And in this case, k, again, is negative 1. So the coefficient on x to the 4th, that's 1. Coefficient on x cubed is 0 because there is no x cubed. Coefficient on x squared is 1. Coefficient on x is negative 3. And the constant is 1. Again, it's important, if any term in the polynomial is missing in the synthetic division table, you show that with a coefficient of 0. That missing term will have a coefficient of 0. And then we start the process. Write -1 in here. And then we begin the process. Bring 1 down. Okay. Multiply -1 times 1. Write it here. And then add 0, -1. You get -1. Multiply -1 times 1. Write it here. Add those two. You get 2. Multiply -1 times 2. And you kind of see how this process evolves. It's algorithmic. That means it repeats itself. The process does repeat itself. Okay, and this was -1. All right, and as you can see, the remainder is 6, which is not 0. Therefore, -1 is not a 0 of this polynomial. Let's take a look at something in a way of a complex solution. Is 1 plus 2i a solution to this polynomial? Again, the coefficients on x to the 4th is 1, on x cubed -2, on x squared is 4, on x is 2, and the constant is -5. All right, and then we do the algorithmic process, bring down the 1, multiply, move up here, add, multiply, move over here, add, multiply, move here, add. And you can see as you go through this, the arithmetic of what I've done here, you can see clearly that the remainder is 0. So that's good. That means 1 plus 2i is a solution. And remember, for complex numbers, I is the square root of -1, so that I squared is equal to -1. Now, because the coefficients are real for this polynomial, therefore, by complex conjugate theorem, the other 0 is going to be conjugate of this one, 1 minus 2i. And we just want to show that if this is a 0 of the polynomial, and clearly it is. And what I'm doing here is I'm actually showing you that if you multiply these a complex number and its conjugate, the product is 5. This was meant to help you with this product right there. And that's how I got the 5 that goes here. This is how I got it. Okay. And well, let's see. So there you go. You have that example. Let's take a look at another example. This example, we have f of x is equal to x cubed plus 4x squared plus 5x plus 2. And we want to see if k equal -2 is a solution. And so I went ahead and did long division by -2 right there. And I wrote the first row of the synthetic division table. Again, the first row is going to be the coefficients that you're seeing here. 1, 4, 5, 2, and they appear in the first row. Okay, and we bring the -2 in here, and the process begins. Bring down the 1, multiply -2 times 1, move it here, add, multiply -2 by 2, move over, add, multiply -2 times 1, move over and add, and that's what you get. So it looks like this one also gives you a remainder of 0. Now, what I had here is that this expression is actually q of x. Okay, or yeah, q of x is the quotient. It's this one. All right, g of x here is just a function. G of x for this example is simply x plus 2. The form is x minus k, but k is -2 minus -2, and that's how you get x plus 2. All right, and there we have that one. Because the remainder is 0, I have this part going to 0. All right, and that is all you have to do for this one. So again, hopefully everything made sense. And we are done with this section. Thank you for watching, everyone.